use IR to find if the if it shows a peak between 2500 to 3500. That means you have carboxylic acid. That shows that benzaldehyde has been air oxidized. The other method, if you have benzaldehyde versus benzoic acid has a lower pH. So by testing pH, you could say if there is benzoic acid mixed or not. Hopefully it's not all air oxidized, because if it's all air oxidized, you cannot change it to, you cannot make it go through this reaction. So you might have like some of it air oxidized. So you can check the pH. If the pH drops, that means some of the benzaldehyde has been air oxidized. Now, the last method you can find out if you have benzoic acid in the mixture or not is to use sodium bicarbonate. So if you have benzoic acid, it will react with sodium bicarbonate. It produces carbon dioxide, so basically it bubbles. And if it's benzaldehyde, it doesn't react with sodium bicarbonate. So we have 3 different methods. If you explain one of them clearly, you get credit for this question, but I want to make sure that you know all the different technique, and each one of them would be correct answer. So you can use either IR, pH, or you could use sodium bicarbonate. If you want to make benzyl acetone, so if you check the reaction again, the product is a dibenzyl acetone. That means 2 benzoic acid for every 1 acetone. But if you want to make a benzyl acetone, that means 1 benzoic acid, 1 benzaldehyde, 1 acetone. Then you would change the ratio. You would use less benzaldehyde, or you would keep the ratio of benzaldehyde to acetone as 1-to-1 ratio. Question 4 says techniques that can be used to purify air oxidized benzaldehyde. So basically you want to, if you have a mixture of benzaldehyde and benzoic acid, you want to remove the benzoic acid, or remove the benzaldehyde, and anyhow you have to separate. Very good. So one method would be vacuum distillation. Why vacuum distillation should be used? Vacuum distillation, basically you're trying to distill benzaldehyde. Very good. Sodium hydroxide is another one. Yes, very good. So basically you're trying to distill and remove the benzaldehyde and leave the benzoic acid. Because they have different boiling point, you can use the boiling point of benzaldehyde is much lower than the boiling point of benzoic acid. You can remove by distillation. But why does it have to be vacuum distillation? Because when you distill it, it can decompose the compound. So when you do vacuum distillation, you make sure that it boils at low temperature. And when it boils at low temperature, it prevents from decomposition. So it's the vacuum distillation. Sometimes I get an answer like vacuum filtration. The benzoic acid is soluble in benzaldehyde, so you cannot do filtration. I just want to make sure that you don't make this, mistake, because with the vacuum, it comes filtration or distillation. In this case, we are using distillation. The other method is extraction using sodium hydroxide. So when you say extraction, that means you are adding which one is that for the distillation, vacuum distillation, Charisse? For vacuum yes, vacuum distillation is used because we want to make sure that distillation happens at low temperature. When you apply vacuum, you lower the external pressure. when vapor pressure of the liquid equals atmospheric pressure, it starts boiling. So if you don't apply vacuum, the atmospheric pressure is 1 atm, and it's going to boil at its normal boiling point. But if the vacuum is applied and the vapor pressure it goes down, then the boiling point happens at the lower temperature. So it boils at lower temperature, and you can do the distillation because you need the vapor of the first compound, but it doesn't decompose. It prevents from decomposition of the substance or the benzaldehyde. It doesn't decompose. The other method was sodium hydroxide extraction. So because the benzoic acid can react with sodium hydroxide and it will change to sodium benzoate, which is water soluble, it comes to aqueous layer and benzaldehyde stays in the organic layer. So sodium hydroxide extraction would be another method that you can use to purify it. Sodium bicarbonate can be used, but sodium bicarbonate it reacts with the benzoic acid, but is not as strong as sodium hydroxide. When it's extraction, it's better to use sodium hydroxide to make sure that all of the benzoic acid is removed. But if it's just purification or neutralization, for neutralization you could use sodium bicarbonate, but for extraction you use a strong base, not a weak base. Next question, if the final product has melting point of 102 to 108. In the pre-lab question, I changed that to 99 to 109, hoping that it would make it more, significant of a difference in the melting point range. And the melting point range is now wide range of melting. And since it's a wide range of melting, that indicates your compound is not pure. I also added explanation to the announcement. So I post the announcement and I said to look for melting point, literature value for melting point of the product. The 82120 is not the literature value. When you talk about literature value, because the melting point must be sharp melting, so it should be like 2 to 3 degree difference. What did you find for melting point of the pure sample? (110 to 111), very good. So if it's 110 to 111, that is a sharp melting point. Now, if you have like a 99 to 109, that's like 10 degree of melting range. And if the melting range is a broad range of melting, that means the compound is not pure. Yes. Okay, since I had a few questions about the pre-lab, and this is the last major pre-lab, really, I wanted to answer these questions. Before I ask you questions or go over the actual experiment. Do you have any questions at this point? Okay, and let me finish with this diagram and the experiment, and then I could answer your question about the lab report. Yes, your question about this experiment, if it's about this experiment, Julia? Okay, then if it's just if it's about the other one, let me finish the sure. Okay, when you look at the mechanism for this reaction, I want you to understand the steps. You don't have to memorize all the steps for the purpose of the final exam for this lab, but I want you to understand every step, at least what is happening in this reaction. Acetone has alpha hydrogen, and what is alpha hydrogen is the hydrogens on the carbon adjacent to CO double bond. So we have alpha hydrogen on left and right side. When you mix that with sodium hydroxide, because alpha hydrogens are acidic, it's going to remove one of these hydrogens. You end up with enolate ion. Enolate ion is just like Grignard reaction. Remember when you have Grignard Mg, like RMgX, the carbon attached to magnesium is negatively charged, and that's why Grignard acts as a strong nucleophile, and it can attack carbonyl group. So the same thing here, when enolate forms, is going to attack the carbonyl group. And when it does attack the carbonyl group, the pi bond is going to break over the oxygen because carbon cannot have more than 4 bonds. You get alkoxide, and you protonate, you get alkoxy group or hydroxide group attached to the carbon, which is known as a hydroxy. So you get the hydroxide here. This hydroxy group is known as a beta hydroxy ketone. And why do we call it like a beta hydroxy? Because the carbonyl group that you have, carbon adjacent to carbonyl group, is known as alpha carbon. That's why I said you have alpha hydrogen here. And you go further, you would use the Greek letters. So you have the alpha, beta, gamma. So it's the closest one or adjacent to carbonyl group is called alpha. Then the next one is beta. Then you have the gamma. So you have the on the beta carbon, you have a OH group. So this is a beta hydroxy ketone, which will go through dehydration. So in the basic solution is not stable. The hydrogen from alpha position is going to be removed by the base, and the OH would leave as a H, and OH would leave as H2O. Then you get alpha beta unsaturated ketone. This compound here is the benzyl acetone. Okay, that's benzyl acetone. You start with acetone, you mix the benzoic acid, you end up with benzyl acetone. Benzyl acetone has alpha hydrogen, and this is going to repeat all the steps. When all the steps are repeated, this compound is going to lose a hydrogen to the base. You get enolate, attacks another benzaldehyde. It gives hydroxy and then dehydrates and gives you dibenzyl acetone. Now, if you look at this mechanism of reaction, you see that for every mole of acetone, you need 2 moles of benzoic acid. What else we can use this mechanism for? Your reactants are acetone and benzaldehyde. So acetone, if you do IR spectroscopy of acetone, the CO double bond would show a peak. Just pay attention to these numbers because that's how you can identify your final product and confirm that the final product has formed. So the CO double bond from acetone shows a peak between 1700 and 1715. Okay. Benzaldehyde, the CO double bond from benzaldehyde, it shows a peak between 1680 to 1700. Okay. So it's going to show a peak between 1680 to 1700. Why the location of CO double bond change coming from acetone to benzaldehyde? Because if you look at the benzaldehyde, CO double bond is attached to benzene ring. What is unique about benzene ring is this pi bonds inside the ring. So CO double bond in benzaldehyde is called conjugated. It's conjugated with the pi bonds. What does conjugation means? It means that is like in simple word, it's adjacent to carbon-carbon double bond. So CO double bond is adjacent to carbon-carbon double bond. This carbon-carbon double bond is attached to another double bond and then another double bond. Alternate double bond, single bond, double bond, single bond, double bond, single bond, double bond. This is known conjugation. What happens when you have conjugation? The location of the peak for CO double bond is going to decrease. So it goes from 1700 to 1680, or the range of 1700 to 1715, it would go to 1680 to 1700. So it would be lower. If you continue this reaction and you come to final product, what's going to happen to the location of a CO double bond for the final product? Is it going to be less than 1680, or is it going to be greater than 1715 or greater than 1700? Is it going to be lower than 1680 or greater? Conjugation would lower the energy, very good. So it's going to be lower, very good. So because the final product is a super conjugated product, you have 4 pi bonds on the right side of CO double bond conjugated, 4 pi bond on the left side, so basically super conjugated. The CO double bond of the final product is going to show a peak at anywhere between 1640 to 1650, so around like 1650 or less. And that is the indication that your CO double bond is conjugated to 2 benzyl group, or is using 2 benzaldehyde, 1 on each side. And to identify the product for this product and the quantitative analysis, the numbers that you need, there would be 1 for percent yield. The ratio of limiting reactant, acetone is the limiting reactant here. Limiting reactant to product is 1-to-1 ratio. And when you are calculating percent yield, make sure you don't count the number of moles for both of the reactant, just the limiting reactant. And it's 1-to-1 ratio to the product. So you find the number of moles of the product and multiply by 234, which is the molar mass for the final product, and you get the mass. That's the theoretical yield. Actual divided by theoretical gives you the percent yield. The other numbers that you need is melting point. It's going to be a sharp, like a strong peak, because it's a CO double bond. It's not going to be broad. Broad peak, it comes from like a OH. That's the result of hydrogen bonding, really, and NH. So the broad peak, it refers to like hydrogen bonding, and the light or the energy is expended there, like spends too much time, and that broadens the peak. But for the other one is basically, we're talking about the strong peak. CO double bond, because it's polar, it would give a strong peak. Okay? So it shouldn't be wide or broad peak. It should be a strong peak. That means that it's really touching it's getting close to the baseline. And I will show you the peak for that, for the CO double bond for the product from the IR spectrum today, that it will pass the 50%. So it's basically touching the baseline. That means it's a strong peak. Weak peak is short peak in this case for IR. Okay, perfect, perfect. A strong peak, very good. Okay, The other information that you need, so one information is the percent yield. The second piece of information you need for the abstract, conclusion, and discussion is melting point. The melting point for the compound, if it's close to the literature value, which is 110 to 111, then if it's close to that number, that means your sample is pure. If it's not close to that number and you have a wide range of melting, that means the compound is not pure. The greater the percent impurity, the lower the melting point is going to be. So if you get a number like 109, 108, then we consider like pure enough. But if you get a number like a 99 or 100 or 102, that would be a impure sample. So melting point. Next, IR numbers. So you have to explain that what peak from the IR spectrum indicates that you have a final product, and have some explanation in the discussion area that the CO double bond, if it appears less than 1660 or less than around 1650, that means it's a super conjugated CO double bond, and that refers or matches with the CO double bond from product, which is dibenzyl acetone. Perfect. Your questions before I move to the IR spectrum or show you the IR spectrum? Do you have any questions?
Doctor, I have a question about what you just said. So basically, discussion area must include a section where you talk about how conjugation affects the what we see in the IR. And
yes, the location of the peak from the IR spectrum for CO double bond. Yes.
Okay, so that should be mentioned, how that helps us identify the final product as the correct or desired final product.
Exactly. Very good.
Thank you.
And also melting point. Melting point, the closer the melting point of your final product is to the literature value, that means that your sample is identified and it is pure.
Thank you.
Because melting point can identify and also determine the purity of the sample as well. So if the melting point, it comes anywhere between like 80 to 120, it's confirmed that the product has formed, but if it's close to the literature value and is sharp, that means your compound is pure.
Thank you.
You're welcome. Any other questions? Questions? No questions? Okay. Julia, you had a question about the report. I don't know, this report or last report? Yes, you can ask now.
Okay, should I do it over audio or?
Either one, either way is fine.
Okay, so it was just with the, like, at the end, whether the product was pure or impure. So the melting point, we talked about when it's lower than the literature value, that would mean that there are impurities, right?
Yes.
But okay, but then when we looked at the IR, it showed the disappearance of the CO double bond and the appearance of the OH bond. So
Okay,
that
very good.
shows purity, right?
Mm-hmm. That is a good observation. The melting point, was it like, how far off was from the literature value? Maybe like 1 or 2 degrees?
Let me look, because I was trying to make sense of this at the end, but
Okay. And let me just explain that when we look at the IR spectrum, if there is any impurity that is coming from ketone, it would show in the IR. Now, if there is impurity that comes from solvent, like if it comes from solvent, that the sample is not completely dry, or if there is a leftover of the inorganic impurity of like sodium borohydride, it still counts as impurity, but the impurity is not ketone if the peak at 1700 completely disappeared. But still, you could say that there's some impurity in the compound. And if it's 2 degrees off, that 2 degrees off, it could be calibration of thermometer, or it could be minor impurity of any sort. It could be leftover of reactant, one of the reactants, or the sample is not 100% dry.
Okay.
And since it's that close enough, then you could just mention as a minor impurity. A 2 degree is not significant number to worry about and look for many sources of error. Or you could say in the conclusion that if the melting point is lower, that means it's impure. That could have been leftover of the reactant or other impurities, or the sample is not dry.
Okay.
Good question.
Thank you. And then can you just repeat again just what you said about like the CO double bond like disappearing with the ketone and like just the purity? Like I guess I didn't learn that part in my in like our class yet, so I was a little confused. You
That's
could
it.
repeat that.
Okay. For the that's for experiment 15 though, right?
Yeah, for the lab report we just did.
Okay. So when you look at the reactant compared to the product, for this reaction here, we have fluoranone versus the alcohol as a product. If you take IR of this, I mean, this area of the benzene ring is the same. See, this area of the benzene ring is the same. This area of the benzene ring is the same for the product. So basically, the IR of the two compound is going to look very similar, with exception to the CO double bond versus OH group here. CO double bond appears at 1700, is a strong peak, but OH appears with around 3300, and it is a very broad peak. The shape is different, the location is different. So if the reactant goes to product, then we take the IR of the product, we don't see a peak that is coming from CO double bond because all of the reactant has changed to product. If you see like a minor peak around 1700, like very small peak, that means there is a minor impurity left over from the ketone. So did I answer your first question first?
Yeah, thank you.
Okay. So if the reactant changes to product and you are taking IR of the product, you don't want to see a peak at 1700. If you are taking IR of the reactant and you know it's pure, then you should not see a peak for OH because this is the reactant. That what makes sense if you have the reactant and product and you kind of compare it, or you look at the balance equation and say, well, in the reactant you would have the CO double bond, the product you have the OH. But we take the IR of the product always because we want to show that yes, the product has formed. Okay, any other questions? You're welcome. Any other questions from the last experiment or this experiment?
Doctor, I have a question about last experiment.
Yes.
So I got my percent yield wrong, and I said it was 51. I believe I got something higher than that. If you could briefly address that and how we end up with 50%.
Oh, that is the percent yield for experiment 14, not 15, right? The one that was just graded.
Titration. What was
Nitration.
Then
Yes,
it was 14.
nitration.
Okay, then
Okay.
never mind.
Nitration. So what percentage did you get?
I believe it was higher than that. I believe 60%. Let me check real
60%.
quick. I can tell you.
I can tell you how you get 60%.
Okay.
If, because I graded few papers and I noticed that if you use 4 milliliters as 0.4 grams, like we use 0.4 milliliters, right?
Okay.
And if you multiply by density, you end up with like 4 point something, 4.9
Okay.
as the mass of the reactant.
Uh-huh.
But if you use as a 0.4 grams instead of the 0.49 grams, then you would get lower theoretical yield. I think you did not multiply by density. I can check your specific.
I got 62.16% yield.
Mm-hmm.
The theoretical
Because,
yield.
yes, because you did not multiply by density of the methyl benzoate. Do you want me bring up your?
No, I just checked it. So you're
You did?
correct.
Okay.
Yeah.
So if you look at your calculation, you see that for yes, you're missing just one step, and that step is to multiply the 0.4 by the density first.
Okay. Thank you.
Let me just double check to make sure that. Yes, you use 0.4 grams. It's not 0.4 grams. It's 0.4 milliliters, but you multiply by the density. Minor.
Thank you. Yeah.
Okay, you're welcome. Okay, any other questions? Okay, if there's no question, I'm going to call for attendance. Next week, it's a spring break, and there is no class. So when you are always home, you don't know what's the difference between spring break and the other weeks. Really, that's why. So next week is a spring break. Week after, we're doing experiment 17 and 18. For experiment 17 and 18, I want you to look at the instruction for assignment for lab notebook. You don't need to write the procedure. Instead of the procedure, you would use the tables that it tells you, it asks you to include. Let me bring that lab notebook for experiment 17 and 18, and I'm going to share that with you so you could see what I'm talking about. Okay, it says for experiment 17 and 18, title of the experiments should be experiments. If you're doing 1 or 2 separate, it doesn't matter. You can do 17 plus 18, or you could do 17 and then 18. Copy the table for IR and NMR values from the experiment 17, and I believe those experiment, let's see, no, I have to check the page number. I want to include the page number, so you is I think 159 to 160 and then 162. Okay, is 159 160 pages. (159) 160 and page 162. This is from experiment 17. Then from experiment 18, it's different. Control C here. From experiment 18, show you. Or that would be page 181, I believe. 181. Page 181. And then classification test is going to be 184, 185. Okay. That's what you include.